Hey there. So getting near the end here. I think I'm just about ready to put the boat monitor into my boat, but it's too cold at the moment. It's going to be another couple of months before I feel like going out to the boat, actually start drilling holes and mounting it in the boat. But what I look at in this video is a redesign of the actual bilge water sensor mount. So I made some changes to that because I'm using an ADC. I also used a resistor ladder, and I show a circuit simulation to get the right values for the resistors I use on that. And then I put the whole thing together and we can have a look at the assembled bilge water level sensor device. As well, did the same thing with our boat monitor case. Pretty much did the final print of that, and also rebuilt the board that has the sensor interfaces on it. It looks a little better now. I may still do another version of that, but I'm fairly happy with it, and it actually works. So I'll show you that all assembled into the case. As well, I updated the MicroPython code that runs on the processor board. I needed to just clean up the code a bit, bring in the two libraries that I showed in the last video for getting the air pressure and ADC values and those things. So that's all in the code, and sending all the values through LTE to hologram. So I have a look at tracing the data as it goes from the boat monitor to hologram and then on to the Firebase backend. And that should be mostly it for this project. I'm going to do one more video after this, just showing the soft setup of our boat monitor parameters to receive the data and some of the visualizations. And then it'll be, like I say, it'll be another month or two before I actually install it in the boat and we can have a look at it working, which will be kind of the final video. Okay, let's have a look at a simulation of the voltage divider I'm going to use. So I can just use one ADC line to see all the switch positions on my bilge water level switch. And this is a simulation. So basically I've got a voltage divider. So I've got 100k coming down from the positive line, and then it's either getting divided by this 100k down here if the switch goes off, or by this 56k if the switch goes off, or by these two in parallel if both switches go off. Just on the bilge switch, normally if there's no water, the switch is on. If there's water detected, if the float rises, then the switch goes off. So let's start the simulation. And you can see this is in the default position of no water in the bilge, so both switches are not being triggered, so they're both on. This represents the lower float, so if that float goes off, it goes up to 1.6 volts, and then if both floats go off, it goes up to the full voltage of 3.2 in this case. It'd be 3.3 in reality coming in from the PyCon board. And then finally the final combination for the switches, although this wouldn't happen in reality, would be the lower float not going off and the upper float still on. So that'd be a malfunction, but I got a separate voltage for that as well, so I can distinctly see what the switch positions are based on the voltage coming back from the sensor. Okay, moving on from the simulation, this is wired up with real components. So I got 100k, 100k and a 56k resistor there. Remember these are probably 5% tolerance. And then with both bilge switches you see here, with no water in the bilge, both these floats are down. So it's measuring 0.848 volts. If the water rises and sets off the first bilge switch, it raises to 1.6 volts. And if the second bilge switch goes off, the water level's going up to that, then it goes up to 3.17 volts. Again, I'm using two 3.2 volts is the power supply for this, and then the final combination of switches, although not a combination that can happen in reality, is if the lower switch doesn't go off and the top switch is on, it measures 1.15 volts. Okay, based on what I learnt from my first bilge switch mount, I made some changes. So I made the actual holder for the switches a little wider, have room for 2 switches in here, so I could align the top switch and the bottom switch differently, and I thought the holes were also useful if I want to run wires up here, so I just ran the holes right through the 2 mounts there. As well, up the top I changed to using a terminal block to hold the wires that are coming up from the switches, still enter the same hole here for wire management, but they'll be going to the block, and as well they'll have resistors on the end to implement that resistance ladder I'm using to read the various switch positions. So now I've got a little hole for holding that terminal block. Generally I just made the actual mount wider and longer, just to give me a bit more room inside to run the wires and make sure the wires didn't interfere with where the actual bracket gets mounted in the boat, and give me a bit more room to run the wires. So just like in the earlier videos, I printed the whole thing off on my 3D printer. You can see it running here. Took about 3.5 hours to print, but that's okay. All the holes are pretty accurate. Okay, so here's the updated build switch printed out and everything mounted again. So I made it a bit wider, a bit higher to give me a bit more room for running these wires. You see the wires now, or the switches are now not aligned one above the other, so it gives a bit more room for these wires to run without possibly interfering with the floats here. And also having the holes in there allows me to use a cable tie to make sure the wires are kept away from anything else, and gives me more room in here to keep the switches away from the actual mounting bolts. The other thing I did was use a terminal block here to terminate the wires from the switches, and I have the resistors that are used in the switch resistor ladder in this shrink wrapped tubing here, so they're different resistance values, so I can detect what actual switch fired off as well. So this is the completed case with everything mounted inside. House power comes in here, plus and minus from the house battery, boat house battery, and the bilge pump sensor is down here, which is basically a simple resistor ladder over the switches in the bilge switch. If I open the top, you can see the 3 boards, power supply, PiCom and PiTrack there, and then the custom component board here, which has the ADC, which is a ADS1115 I2C sensor, and then the temperature, humidity and pressure sensor is in this little housing out here, again connected through I2C. The backup battery is here underneath the PiCom board, and the final thing to look at is I have this wire here coming from the house battery, and that's going through another voltage divider and is being read by one of the ADC channels, the A0 channel, to keep an eye on the house battery voltage as well. That all seems to work. Aerials down here, I've had this running for a while. All the sensors seem to be working, sending data through LTE, then through hologram, and it's been received at my boat, our boat monitor back end on Google's Firebase, and then my Angular applications giving me the information coming from these sensors. So I updated the Python, MicroPython code that runs in the our boat monitor hardware. So I'll just run through that. So you saw in the previous video I played around with these 2 libraries, the BME 280 for the temperature, humidity and air pressure, and the ADS 1115 for the ADC chip that reads voltages. So looking at the main application, main.py, I'll just go through the changes I made here. So when we first get in, I just turn off the heartbeat so we don't have the blue LED flashing through while this is running. Then I added flags mainly to help with testing, but to enable different functions in the code as it goes through. So whether to include GPS, whether it goes through the GPS collection routine, whether to include BME 280 or the ADS 115. So I can turn those on and off separately. Whether to send data through LTE. Sometimes I just want to test it, but not want it to actually send the data through LTE. To set up the deep sleep cycle time. So by default I've got it for an hour, which is what I'll have it running on the boat. But again, for testing I may make that just a few seconds, just to be able to test out the sleep times without having to wait for it to go through a whole cycle. I've added this ADC 0 or port 0 voltage ratio, and you can see this came from the calculation that I did on the voltage divider. So this is what I need to divide the voltage by to change it back to the real world voltage, what it would see if it hadn't gone through the voltage divider. And I needed that for the house battery, where I'm dividing it by down to about 10% of the size, just because the battery voltages are higher than the 3.3 volt maximum volt of the ADC, but I want to multiply it back and send the true voltage back to the back end system. Also got a flag in here to whether I want it to go through the sleep routines or not. Sometimes for testing I just want it to drop through once and then return me to the Py command or the Python command prompt. This code was in our LoRa project, so this should look familiar if you've seen that project and the other set of videos. So getting an object for the PyTrack board, getting an object for the this board, and setting up the wake up times and the sleep. I'm turning off the accelerometer. I'm not using that, just to save a bit of power. Do a garbage collection here just to make sure memory is looking as good as it can do. I set up this array called data list, and this is going to be the values that get sent back through LTE, and we can see how that gets populated as we go through here. Then the first piece of sensor data I'm going to get is the lithium-ion battery voltage. So this is the battery that keeps our boat monitor running even if the house battery's turned off or runs down. So I just do the Pi read battery voltage to get that, and they'll give me the battery voltage on the lithium-ion battery, and I can set up a trigger, so if it goes below about 3.4 volts, I can send alerts, or even if it goes below, say 3.7, which is kind of the normal reading for the lithium-ion battery, if it goes below that, it sends an alert to say the battery's being used. I do if I include GPS, it goes through collecting the GPS information. And you'll see here in the data list, one thing I had to do was, if either I don't get a GPS result coming back from the GPS, or if I'm not including GPS, I've set the flag not to include GPS, I still want to include that value or that entry in the data list array, but I just include the values with a value of 0. Okay, so those devices, the lithium-ion battery, voltage sensor, and the GPS, run through the existing I2C interface that's built into the PyTracker board. So my external sensors use I2C as well, I2C, but that's running off the second I2C interface using pins 10 and 9. And again, previous video to this one I show more details how I set that up and how I'm interfacing the squared C interfaces, but once I've got an I squared C object here, then if I'm including getting results from the BME 280, so temperature, pressure and humidity, then I just go out, retrieve those values and then add them to the data list. If I'm not getting them, then I just create dummy values with zeros in the data list. And same thing for the analog to digital converter. So I'm using 2 channels of that. So again, I connect to it through my I squared C interface, and I get the voltages of the first interface and the second interface on the 1115, and you can see here's where I use the ratio to multiply out the voltage I get off interface 0 to convert it to the real voltage. Again, if I'm not using the ADC, then I just set those to dummy values. I just deinit the I squared C interface at this point, just so I don't keep starting it up and it's not active during the sleep. I do the send data if I have the send data flag set, so send data to the hologram, and I'll show you that in a sec. And then I can go into the sleep routine again if I'm doing do sleep, and so they'll power down the whole device for an hour. Now I've got that that code running, and I'm seeing the data come through hologram, which is my back-end service for receiving the LTE data and sending it on to our boat monitor Firebase backend. You can see here in for this particular device just a summary of what's been going on. So I've been running it for a few days now. So things I had to do under route. So we saw this outboat monitor route in the previous video, but just a little more detail so you can see in here in the payload. I have all the new fields, so ADC. So these are all the things that I put into the data list in the code. So they get sent through to, all these values get sent through to hologram, and this route converts them to a string that gets sent onto the our boat monitor backend to be processed in the collection function. We can actually see the data coming here, what it looks like. And this is getting set on to our boat monitor. And the data that's sent on from hologram to the back end of Firebase gets processed by the functions that I showed earlier in this series of videos, and gets, if there's a matching parameter in the data coming in, it gets sent to the event collection in the data store. And let's have a look at what the recent ones are. So I can just look at the timestamp and do a descending sort, apply that, and if we look in these, we see some of the values being sent through. So like air pressure, that's the value in Pascal. Humidity, that's the percentage value, 32%, so it's reading it inside my house at the moment. Lithium ion battery voltage, I've got the device running on the lithium ion battery at the moment, so that's got a voltage of 3.176. So everything's getting recorded in the events. And I'll wrap this video up for now. I'm going to do one more video after this, just showing how I set up the Our Boat monitor to actually collect these events, what parameters I need to put in to match the values that were coming in from hologram to get these event records made. And then we'll look at some of the data. Like I've said, I've had this running for a few days and been collecting values, so we can look at the data as it gets displayed in the Our Boat monitor application, and then we can look at what else is left to do.